solve this inequality. And we have an x to the fourth. So we're going to have to find two solutions to get it down to an x squared. We want to start with the possible rational zeros. So it would be 1, it'd be 2, it would be 4. Keep on going. To save some time, I'm going to cheat. And the first one we'd come across is 2. 2 would work. So let's plug 2 in synthetically. We have 1, 6, 4, negative 24, negative 32. Let's bring down the 1. We got 2, we got 8, we got 16, we got 20. 40 gives you 16, and then that is 32, and we have a remainder of 0. So 2 would work. Then 1 to 8 is not the same as 5 to 4, so this does not factor by grouping. Unfortunately, that would be nice. But then we have, as possibilities with the 16, we'd have 1, we'd have 2, we had 4, keep on going. And the next one that would work would be negative 2. So we'll plug negative 2 in synthetically. We got 1, negative 2, 6, negative 12, 8, negative 16, 0. And now we have what we want. We want an x squared plus 6x plus 8. We want an x squared. So we have x plus 2, x plus 4. Well, we also have, we got negative 2 makes this x plus 2, 0. And we have another one of those. So really we have 2 of these. And we also have an x minus 2 if we had the factored form. And what's nice about the factored form now is we see that 2 counts once, negative 2 counts twice, negative 4 counts once. So let's put this on a number line. Negative 4. We have negative 2 that counts twice, negative 2. And we have 2 that counts once. We do not want this to equal 0, which means I cannot include any of those. Now this is a polynomial, so we can talk about ending behavior. The ending behavior of x to the fourth looks like x squared. It acts like x squared. So on the ends of these zeros, it's going up on both sides. Then cuts through negative 4, bounces off a negative 2, and cuts through 2. So that's the nature of the graph. Of course, this is not perfect, but we don't care. We just need the positives and the negatives. Now, we want less than 0, so the answer is negative 4 to negative 2, and negative 2 to 2. Now, if I change that just slightly, and we're done with the problem, by the way. It's over. But if I change it to less than or equal to 0, I would go from negative 4 all the way to 2. And I could include those. So since you could include negative 2, you wouldn't really have to skip over. You just include it if zeros are included. Any questions on that slight adjustment? Now we have a rational one, so we go from polynomial to rational. We need common denominator. Well, first we need to compare this to 0. So we have 12x plus 65 over x plus 4 squared minus 5 is greater than or equal to 0. So we get one side compared to 0, and then we multiply by x plus 4 squared, because that's the common denominator. Well, it's really the only denominator on this one. We have a little bit of work to do with if the denominator is x plus 4 squared. Let's multiply out the x plus 4 squared. So we get x squared plus 8x plus 16. Let's distribute the negative 5. So we have minus 5x squared minus 40x minus 80. Collect all the like terms. So we have negative 5x squared. 12x and negative 40 is negative 18x. No, 28, not 18, 28. And then 65 and negative 80 is minus 15. Now we can take a negative out of that, and it's 5x squared plus 28. I really want to make that 18 apparently. So plus 28 plus 15. We have 5x and x. And then if we have plus 5 and plus 3. We get 25 and 3, which is 28. However, I can't forget that I have this x plus 4 squared, and that's greater than or equal to 0. So if we're just doing a lot of work on the top, I don't see why we have to keep writing the denominator over and over again. But if you're going to do that, make sure you don't forget that it's there. It would follow along. Well, now we want all the zeros. So x equals negative 3/5. X equals negative 5. Those are the zeros. But then we want what makes the denominator 0, so where the function is undefined. And that's x equals negative 4, but we can never, I don't care what the inequality says, you can never include what makes the denominator 0. So we will not include negative 4. Let's get the number line. We got negative 5, negative 4, negative 3/5. I can include the negative 3/5. I can include the negative 5, but not the negative 4 because that's in the denominator. Well, we have to test some points. How about negative 6, negative 4.5, which is negative 9/2? How about negative 1, and how about 0? I could do negative 3, but negative 1 is probably even easier. So let's plug negative 6 in. We get negative 30 plus 3. That's certainly going to be negative. Negative 6 plus 5 is negative. And look, the denominator will always be positive because no matter what we get, we're going to square it. That's going to be positive. But you got to be careful because we got this extra negative out here. So negative, 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 negative. Negative 9/2. Well, we got to work a little bit with fractions. Negative 9/2 times 5 is negative 45/2 plus 6/2. I know what the value is, but I only care that it's negative. We get the extra negative out front. Negative 9/2 plus 10/2 just makes it to be positive over positive. So negative times a negative looks like positive. Negative 1, we get negative 5 plus 3, that's negative. Negative 1 plus 5, that's positive over a positive. But the extra negative out there makes everybody positive. With the 0, we got positive, 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 but that negative makes everything negative. We want positives and equal to 0. That means the answer is negative 5 to negative 4. Negative 4 to negative 3/5. And I don't care if it would have said equal to or not equal to. No matter what, we would not be able to equal that negative 4. We'd have to skip it no matter what because it makes the denominator 0. Any questions on this one? Find the domain. Well, when we have even radicals, negatives is a problem. We cannot take the square root of a negative. You can't do that, right? So x squared minus x minus 6 has to be greater than or equal to 0. We can take the square root of 0. Square root of 0 is 0, no problem. Let's factor this. X minus 3, x plus 2. So x equals 3, x equals negative 2 for the zeros. And I like parabolas because they look like that. That's another polynomial. And not only is it a polynomial, it's a parabola. No problem. I know what those look like. Now we want those to be positive. So we have negative infinity to negative 2, bracket, and then 3 to infinity. This graph is positive on the outside of those two zeros. I don't need the plural there. Didn't need it. Third root. Positives and negatives don't matter. You can take the third root of a positive. You can take the third root of a negative. Odd roots don't matter. However, denominators always matter. We have to look at x plus 3 and x plus 1. Now, I got it. Now, since I don't care whether it's positive or negative, I don't have to do a number line here because the domain is negative infinity to negative 3, union with negative 3 to negative 1, union with negative 1 to infinity. So on this one, because it's the third root, I just have to skip over what makes the denominator 0. Now, if that was a square root or a fourth root or a sixth root, I'd have to go through the whole process. So I wanted to show an odd one as well. Those are a little easier. I have a correction on this one from what I printed out. That should be +6 instead of +1 on your paper. If you're watching this video at home, it's just going to be a +6, so no changes necessary. I had to talk to my audience there for a second. X plus 2, x minus 1 over x plus 2, x plus 3. So first step is factor anything we can factor. Cancel, cancel. That means we have a hole at -2. The hole is at -2 comma something. We plug negative 2 back into what remains, which gives us -3 over 1. So -3. We have a hole at -2, -3. Now we do all the information on what remains. We don't go back to the original. X-intercept is 1, 0. Y-intercept is 0, -1/3. When we plug a 0 in, we're left with -1 over 3. We have the point 1, 0 and 0, -1/3. Vertical asymptotes, that's what makes the denominator 0. So -3. Horizontal asymptotes is a comparison of the powers. We have an x over an x, so we have a 1 over a 1. That means we have y equals 1. Extra points. Well, I probably don't need any extra points on the right side of the vertical asymptote. We got plenty to go around there. But I have nothing on the left side. So how about we plug in -4 comma something. Now -4, we're going to plug that into what remains, which is -5 over -1. So it's 5. -4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep, right here. Now, we really don't need a whole bunch of points to know what it looks like, because we're just doing these kind of in general anyway. So once you get that point on the left side, just draw that smooth curve to the asymptotes. I'll bet if you graphed it, it'd be very similar on a calculator. Now, as far as the domain, we have to skip over vertical asymptotes, which is at -3, and we have to skip over holes. The graph does not exist there. -3 and -2 make the denominator 0, whether it's a hole or a vertical asymptote. I think on your paper on this, on the next one, it says -1. It should say +1. So please make that change. +1 on the end. If you're going to try to factor this, you'd probably have to find the zeros unless you know the pattern. There's a pattern going on here, and this is actually x plus 1 to the third over x plus 2. So you'd have to probably do some synthetic division to find out that -1 counts 3 times. Hello. X-intercepts, that's what makes the top 0, so -1, 0. Y-intercept, we plug 0 in for x, and we get 1 to the third, which is 1 over 2, so it's 1/2. We have -1, 0, 0, 1/2, right there. Vertical asymptotes, that's what makes the denominator 0. So x equals -2. Here's our vertical asymptote. Horizontal asymptotes, we have none because the top power is bigger than the bottom power, so this thing is shooting off to infinity, on the right at least. Slant asymptotes, here's why I show this one, because there are none. There are no linear asymptotes on this, not horizontal, there's a vertical one. And the reason I know that is because the top power is 2 more than the bottom power. Now, when we divide this synthetically, and we can divide synthetically because the denominator is a linear, we get 1, 3, 3, 1. When we do this, the result is not a linear equation. It's not a line. It's a parabola. So we have a parabolic asymptote. Bring down the 1, -2, 1, -2, 1, -2, -1. On asymptotes, we ignore the remainder. So we have an other, I guess, happens to be parabolic. It's y equals x squared plus x plus 1. And you can have x squared asymptotes, you can have x to the third asymptotes, you can have any kind of asymptote. It doesn't have to be linear. That's the only thing you've ever seen, but that's not the only ones that actually exist. All right, so now we have a little extra work to do. To graph a line, no problem. You got the y-intercept, you got the slope. Well, now we have to go back to our skills of graphing a quadratic. The vertex, the x-coordinate of the vertex is negative b over 2a, negative 1 over 2. So it's negative 1/2 comma something. So negative 1/2 comma, well, you get the something by plugging it back into the original, which is 1/4 minus 1/2 plus 1. 1/4 minus 2/4 is negative 1/4 plus 1 is 4/4. So it looks like 3/4. 3/4. That is the vertex of the parabola. So negative 1/2, let's do this in another color. Negative 1/2, 3/4. It's about right there. Now if the a of your parabola is 1, like it is in this case, 1x squared, you can follow the pattern of squaring numbers. Over 1 up 1, 1 squared is 1. Over 2 up 4. Over 3 up 9. You could do that forever. Over 4 up 16. And that'll be your parabola. Now we can do that pretty easily, like I said, because a is 1. So over 1 up 1. Over 1 up 1. Over 2 up 1, 2, 3, 4. Over 2 up 1, 2, 3, 4. And then, now remember this is an asymptote, so we want this dotted. And the asymptote looks like that. Now we got to remember that the graph follows this asymptote. So on the right side of the vertical, I pretty much have it. It's probably going to do this here, and then it's going to kind of take the shape of this parabola. Just like if it was a line, it would start taking the shape of a line because it would start flattening out. But it never does touch that asymptote. Well, I have the right side of the vertical covered, but what about the left side of the vertical asymptote? So here's where the extra points come in. Negative, let's see, what do I need? Negative 3. Negative 3 comma something. Well, let's plug that into the factored form. We got negative 2 to the third over negative 1 when I plug a negative 3 into this. Well, that's negative 8 over negative 1, so it looks like up here at 8. Negative 3, 8. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. That's right there. So look at this vertical asymptote right here and this parabolic one. So it's kind of in this corner. So it follows that parabola going up. It's got to dip down here somewhere. I don't know exactly where. And then it's got to go up and follow that asymptote. There's nothing else that it can really do.